Okay, so we talked about measuring the standard cell potentials under standard conditions, but I want to introduce an equation for how we would deal with cell potentials under non-standard conditions. So this equation is called the Nernst equation, which allows us to calculate the standard cell potential under non-standard conditions, which can be more common, right, than standard conditions. So we include the reaction quotient Q, which makes the free energy change dependent upon the composition of the reaction mixture, right? So our equation becomes, right, so cell potential, right, which is not under standard conditions, is going to be equal to whatever the standard cell potential is minus RT over NF times natural log of our reaction coefficient. So if this reaction is done at standard temperature conditions, right? Not necessarily standard conditions across the board, but standard temperature, 25 degrees Celsius, then this equation is reduced to this, right? Where we just plugged in 298 Kelvin for our temperature and we get this equation here. So let's look at an example. So use data from Appendix L. Appendix L has our standard reduction potentials. To calculate the standard cell potential, the standard free energy change, and equilibrium constant for the following reaction at 25 degrees Celsius. So we're going to calculate all three of these properties that we talked about. And then we're going to comment on the spontaneity of the forward reaction, i.e., is it spontaneous or non-spontaneous? And we're going to comment on the composition of the equilibrium mixture of reactants and products. So as we move to equilibrium, is the equilibrium mixture more consist of more reactants, more products, or equally? So here is the redox reaction that we are looking at. So first, right, let's determine what is our reaction at our anode and cathode. What is our oxidation half reaction and our reduction half reaction in this redox reaction? So iron is being oxidized, silver is being reduced, right? So we have, looking at Appendix L, we have our standard cell potentials, standard reduction potentials for each of these half reactions here. And already we've multiplied this half reaction by 2 to make sure that our electrons are balanced out. So then when we add our overall redox reaction and then we add up our cell potentials, or we do that of the anode, the cathode subtracted by the anode, we get an overall cell potential of 1.247 volts. So this is our standard cell potential for this reaction. So since 2 electrons were transferred, N is equal to 2, and we can determine the equilibrium constant using this reaction here, right? We can use this reaction because the temperature is done at 25 degrees Celsius. And we've calculated our standard cell potential here, so we just plug that in. We plug in 2 for N and we solve for K. So when we solve for K, we get 1.3 times 10 to the 42, a very large K value. And from that, we can calculate our standard free energy using this equation here. So we plug in 2 for N, Faraday's constant, our standard cell potential. We get negative 240.6 kilojoules per mole. So here are all three of the values that we've calculated. We have a positive value for our standard cell potential. We have a K value that's really large. We have a negative delta G value. So the reaction spontaneous. right? Because we have a negative standard free energy and a cell potential that's positive. Since K is very large, this indicates that the equilibrium mixture consists mostly of products. Mostly of products.